Hello all, a very good day to all of you. In this session, we will discuss all the questions that have come from analog circuits in 2017 set 1 GATE examination for electronics and telecommunication branch. Okay, so there are two sets of exam in 2017. So we will discuss about the set 1. Okay, so in set 1 in 2017, there are 7 questions, right? 3 are of 1 mark and 4 are of 2 marks. So total 11 marks have been asked from this particular subject in 2017. Okay, so let us discuss all the questions one by one. The first question is, for the operational amplifier circuits shown, the output saturation voltage are from plus 15 to minus 15. Okay, we have to find out the upper and lower threshold voltage for the circuit. Okay, so first let us understand what does it mean. Okay, see, since we see there is a feedback from output to positive terminal, so it is operating in positive feedback. Okay, when a op-amp operates in positive feedback, it behaves like a comparator. So it behaves like a comparator. Right? That this implies if the potential at the positive terminal is greater than my negative terminal, then V out is equal to plus V saturation, or here it is 15 volt. Right? So if this is the one condition, then second condition is if V plus is less than V minus, okay, then my V output will be equal to minus V set. Right? In this case, it is minus 15 volt. Okay, then what is called upper and lower threshold voltage? Okay, so what do you mean by upper and lower threshold voltage? Suppose my V out is equal to upper VTH. Suppose my V out is equal to plus 15, right? Then what is the input, right? That will change my output from plus V set to minus 15. That means plus 15 to minus 15. Right? Suppose presently my output is plus V set, then at what input voltage my output will change from plus V set to minus V set. That is nothing but my upper threshold voltage. Okay. See, in this question, suppose my V output is equal to 15 plus 15. Okay. So let us generalize it. Suppose, so I want to know what is the voltage of V in that will change my state from one state to other state, right? Suppose my V output is 15 volt. Okay. And when will my V output will go from plus 15 to minus 15? When my voltage at the negative terminal, right, will be more than this potential called suppose VTH plus. Okay, VTH. Okay, so if my V output is 15 volt, there will be some voltage at this particular node, nothing but a positive terminal. Okay, then to change that state, my V negative should be more than V positive, right? V negative should be more than V positive. Then only I can change my state to plus V set to minus V set, right? So if my output is 15 volt, what is in the VTH now? VTH, let us put a nodal equation at this point. Okay, so VTH minus V out is 15 by 10K, right? Plus VTH minus 3 divided by 5K is equal to 0, right? This implies VTH 2 VTH minus 30. I multiply both sides by sorry, multiply both sides by 10k, then it will be VTH minus 15 plus 2 VTH minus 6. I multiplied both sides by 10k, so this 10k get cancelled, 5k 10k 2 times you will got, so I got this one. Okay, this implies VTH plus 3 VTH is equal to 15 plus 6 is equal to 21. This implies VTH is equal to 7 volt. Okay, so when my output is at 15 volt, then the potential at positive VTH is nothing but V positive, right? So when my V output is 15 volt, at that time my potential at the positive terminal, nothing but my threshold voltage of upper threshold voltage will be 7 volt. So if my input will be, if V in is nothing but V negative will be greater than this V plus here is 7 volt, then I will switch my state from plus 15 to minus 15. So here the VTH upper equal to 7 volt, right? Then if my input will be greater than 7 volt, then my output will changes to plus 15 to minus 15. Okay, now what is lower threshold? Lower VTH. Suppose my output is at minus 15, right? Then what is the input voltage that will change my output from minus 15 to plus 15? Okay, then you will have to calculate. Suppose output is minus 15, then I have to calculate this is VTH. Okay, negative side, so it will be VTH minus 15 is equal to plus 15 divided by 10k plus VTH minus 3 divided by 5k is equal to 0. Similarly, multiply both sides by 10k, so we'll get VTH plus 15 plus 2 VTH minus 6 is equal to 0. This implies 3 VTH is equal to minus 9. So VTH is equal to minus 3. Okay, so when my output is at minus 15, at that moment my V positive is equal to VTH is equal to minus 3 volt. Okay, so if I want to change my output from minus 15 to plus 15, then my V input, okay, should be greater than V positive. Sorry. So if I want to change my output from minus to plus, then my V negative should be less than VTH or V positive, right? Then only my output will change from minus 15 to plus 15, right? So V negative should be less than VTH is here is minus 3 volt. Okay, so this is the condition to make my output change from minus 15 to plus 15. So here VTH lower will equal to minus 3 volt. Okay, so upper is plus 3 plus 7, right? Lower is minus 3. So answer should be B, right? This is an easy question. You have to understand, but how to change the state. Okay, let's go to the next question. A good transconductance amplifier should have. Okay, first to understand what is transconductance. A transconductance means output is current and input is voltage, right? A amplifier which takes input from a voltage source and convert it to a current which will be proportional to my input voltage. Transconductance, it is converting my input voltage to output current. The output current is proportional to my input voltage. Okay, that is a transconductance amplifier. So what it does, my transconductance amplifier, suppose it is, okay, what it does, whenever there is an input, right, V in, there will be some source resistance of the source Rs, then it is taken by my Rin is my amplifier input resistance, right? Then it takes the voltage from V input to the amplifier. Then at the output, it generates a current, right? Generate a current that is proportional to some constant amplifier gain into V in. Here it is, suppose Vs, here it is Vn. Okay, it gives a voltage Vn. Okay, and this should have some, since it is a current source, it have some output resistance Rho, then it gives current to my load. This is my RL, right? So this is plus minus V0. V0. Okay. So what it does, it takes supply from my input voltage, input source, then it converts my input supply to a output current proportional to my input voltage. Okay, and we want most of the output current should go to the load current. This is my load. Okay, so for this you see, since I want almost all of my source voltage should come into the amplifier input, so I want my Rin should be very high, right? Very high compared to RS. Then only it will take almost all of my source voltage into the input of my amplifier. Okay, this is my amplifier. Okay, so Rin should be very high. Here also I want the current at the output, nothing but AN to VN, should go almost completely to my load resistance, right? So in that case, my load resistance should be very small compared to my output resistance, right? So then only my total current will pass to my load, right? If my load resistance is very high, then what will happen? Some of the current will go through my output resistance, okay, which will be dissipated, right? So I want all of the output current should go to the load current. At that time, my load current should be, load resistance should be very small compared to the output resistance. So my output resistance also should be very high. Okay, so high input resistance and high output resistance. Here it is given high input resistance and output resistance. So I answer to C. Okay, since for high input resistance, in order to take whole of the source voltage to the input, and high output resistance in order to deliver all the load, all the generated current A into B in to the load. Okay, let's go to the next question. You see, the Miller effect in context of common emitter amplifier explains. Okay, so if you see, if you have a common emitter amplifier, right? I'm just drawing some common amplifier. Okay. V output. Okay. So what happens, right? If I go to very high frequency, right? Very high frequency, the equivalent circuit of my common emitter amplifier looks like this. Okay. What is there? There between base and this is collector, there will be some capacitor. Okay. It is called intrinsic capacitor. Okay. That will comes into play when my frequency is very high. Okay. Why? Because you see the CC, C and CCC are the intrinsic capacitor. It's not the external capacitor. Okay, intrinsic capacitor. Okay, which are very small, right? Which are very, see, the intrinsic capacitor is there in the transistor irrespective of my frequency of operation, right? This intrinsic capacitor CC is nothing but capacitors between base and collector. Okay, between this and this, I have a capacitor CC. Between base and emitter, I have a capacitor called CE. Okay, these are there starting from DC to a higher frequency. But the thing is, since the value is very small, right? The value is very small. The impedance is nothing but J into 2 pi F into C, right? So since they are very small, okay, if my frequency is very small, then 1 by small into small into small, 1 by small to small will be very high. So in lower frequency and mid-band frequency, even if the capacitors are there, they will not affect so much to the operation because the value is very high. I can treat them as a open circuit. Okay, so the intensive capacitor which are there in the transistor will not come into picture in low to midband frequency because the impedance offered by them is very high in low frequency and midband frequency. Okay, if I go to very high frequency, right, then what will happen? This frequency will be very high. Okay, so high into small, then this total value will start noticeable. Okay, so they will come into effect. Okay, and what will then what they will determine? They will determine my high frequency cutoff. Okay, so if you see my gain versus frequency, in low frequency there is a gain in drop because of the input capacitor and the coupling capacitor. Then there is a midband gain. In this range, the coupling capacitor will be like a short circuit and the intensive capacitor will be like a open circuit. Okay, in this. Then if I go to high frequency, right, in high frequency, these capacitors will start affecting their behavior, but the impedance will go on affecting my behavior. So since the impedance will start noticeable, what will happen? My gain will reduce at the high frequency. So this high frequency gain reduction is due to the intensive capacitor that is there in the BJT, and this low frequency is because of the external capacitor, that coupling capacitor, the bypass capacitor. So all this is C input, the input capacitor, right? C input. So these capacitors are external, which will affect my low frequency of operation, and this will be done by this high frequency intensive capacitor. Okay, so what is telling the Miller effect, right? So because you see there is a capacitor between my input to output CC. Okay, because of Miller effect, at the input my capacitor will be C plus CC into 1 plus gain. Okay, so if you see at the input, the effective capacitor by the CC will be multiplied by 1 plus gain. Okay, so at the input I have a very high capacitance because of Miller's effect. Since the capacitance between base and collector, nothing but input and output, will get multiplied by 1 plus gain times. So my input capacitance will be very high. It will be C, suppose C input, okay, will be increasing because of Miller effect. So since capacitors are increasing, my bandwidth, okay, is proportional to 1 by C into the R. So since C is increasing, right, what will happen? My bandwidth will decrease. Okay, so it will decrease my high frequency cutoff frequency, right? So high frequency cutoff frequency will be determined by these capacitors. Since the CC is getting multiplied by 1 plus gain, if you look from this input side, so since CC is increasing, my bandwidth will reduce. Okay, so what is the correct answer? The Miller effect will reduce my high frequency cutoff. This is the answer. Then is a 2-mark question. In the figure shown, right? In the figure shown, what it is asking? There is an NPN transistor act as a switch, right? Okay. For the input voltage shown in the figure, yeah, the transistor switches between cutoff to saturation region operation when T is large. When T is large, T is the time period. This T, okay, this T. Assume that collector to emitter voltage in saturation is DC saturation is 0.2 volt, right? And VB equal to 0.7 volt. Then we have to find out what is the minimum value of common base current gain alpha. Okay, alpha is common base current gain is nothing but IC by IE, correct? Of the transistor should be. So what it is asking, right? We have to select which kind of transistor so that for particular this input it will behave like a proper switch. What it mean? When input is high 2 volt, it should go to saturation, right? So for that the transistor should have how much minimum common base current gain alpha. So we have to select a transistor of minimum what value of alpha so that for the input voltage I am applying, it will go to saturation. Okay, so for this, let me just explain very briefly about what is a saturation. Okay, then only it will give a understanding, it will give a visualization of what is the minimum value of common base current gain. Okay, so you see, if you take a NPN transistor, right? This is NPN. Okay, NPN. This is emitter. This is base. This is collector. Okay, so we know, before understanding saturation, first we have to understand what is a active region. Okay, in active region, guys, you see, this is my emitter, this is my base. This is base, this is collector. So NPN, so N should be I. Okay, this is my active region. Right? In active region, VEB, okay, emitter base junction is forward bias, and base collector junction reverse bias. Okay, then I can say my transistor is in active region. Okay, in active region, you just little bit understand about the what is the operation. Okay, so whenever I forward bias a PN junction, right? This is nothing but NP, right? PN junction. Whenever I forward bias a PN junction, there will be injection of electron from emitter to base, and there will be a injection of hole from base to emitter, right? So if I want to draw, since there will be injection from emitter to base, they will be injected depending upon my input potential and also the doping in emitter, base, and collector. Okay, so depending upon my doping, they will be injected from emitter to base. So if I want to draw the carrier profile, right? Carrier profile means nothing but the electron profile in base region. Okay, so this will be like this. Okay, approximately will be like this, because the electrons are injected from emitter to base. This is nothing but my this is nothing but my electrons and in base region. Okay, this will be injected from emitter to base. Similarly, there will be injection of holes from base to emitter. Since generally the doping of emitter is very large compared to base, so this value, okay, this value will be little less here. Okay, so this is my injection from base to emitter. These are nothing but the concentration of holes in emitter region, right? So you see, and in collector, since it is reverse bias, right? Reverse bias, you know, in reverse bias, the carriers will be, suppose this is N region, right? N region. So this is P in collector. There will be little bit reduction, right? In, because this is reverse bias, right? In reverse bias, so whenever there is a forward bias or reverse bias, the carrier concentration at the junction will be proportional to exponential of NB0 in zero bias into exponential of VEB by VT. Okay, so whenever I apply forward bias, it will be NB0 into exponential of VEB by VT, right? So what happened? What I'm telling, the carrier concentration at a junction will be proportional to whatever it was there before into the exponential of the reverse, exponential of the bias I'm applying. Okay, so since it is -1, okay, since it is VCB is very much negative, so this will be almost 0, so it will be negative here. Okay, so what is happening, you see, since in forward bias the emitter base junction is forward bias, there is injection of electron from emitter to base. So and in base region, you see, because there is a concentration gradient, right? Concentration gradient, what will happen? The electrons will be diffused, okay, like this, and will generate a current, because these electrons will be attracted by the reverse bias junction, right? So they will diffuse to this junction, and in this junction they will be attracted by the applied electric field of outside. Okay, so the electrons will be diffused from this base emitter junction towards the collector base junction because of concentration gradient. Then in this junction there is a field, so they will attract the electron. So the current here is because of diffusion in the base region. This is called a collector current. Okay, so this is the situation in active region. Okay, so if I just want to show you how it happening, you see the current is nothing but electrons will be injected from emitter to base. Then here, because there are a lot of holes, there will be some recombination, right? And almost all the current will flow from base to emitter because there is a concentration gradient, and also in the junction there is a field which attracts the electrons. Okay, so a base current is consisting of the current that is injected from base to emitter, nothing but holes, plus my recombination current. So my base current will be IB is equal to IB1 plus IB2. IB2 is nothing but recombination. Okay, IB1 is because of injection from base to emitter, injection of holes. Okay, this is the condition in my active region. Okay, so what will happen if I go to saturation? In saturation, VEB will be same forward bias, but what will happen B to BC? It will be reverse. It will be again forward bias. So in active region, VEB will be forward bias and VBC will be reverse bias. But in saturation region, VEB will be remaining same as forward bias, but VBC will be again forward bias. It is converted from reverse bias to forward bias. So what will happen? You see. Okay, what will happen? You see, because the carriers will be injected from emitter to base will be remaining same because it is forward bias same as previously. So the injection of carrier from emitter to base will remain same, right? Similarly, the injection of current from base to emitter also will be remaining same. Okay, what will change? Okay, so this will remain same. Okay, and the injection also will remain same. What will change? Let me change the color. What will change? Since base and collector will be forward bias, what happened to this is there will be injection of electron from collector to base because this since I changed it to NPN, I change it to forward bias, there will be injection of electron from collector to base, there will be injection of holes from base to emitter. Okay, so what will happen across this junction, right? The electron will be emitted from collected to base. So if I draw, what will happen? Again, there will be some injection like this. Okay, this is because of this is because of one. This is first case. Okay, second is this is the second case. Okay, so and there will be injection of holes from base to collector. So there will be injection of holes also here. Okay, this is second case. So if you see there is injection of electron from emitter to base, again there is injection of electron from collector to base. So there is a lot of carrier in the base. So why it is called saturation means because there are the base is saturated with a lot of carriers. There is injection from emitter and also from collector. So base is saturated with carriers. That's why this is called saturation region. Why it is called saturation? Because the base is overloaded with carrier. Okay. So if I want to plot the total concentration in base, okay, how it will be? Will be sum of 1 and 2 will be the concentration in base. So here it will be same, but if you come like this, it will be like this. You just add 1 and 2 to get 3. 3 is nothing but the total electron concentration profile. profile. Okay, profile will be concentration because of injection from emitter to base. This is emitter to base plus because of injection from collector to base. Okay, if I add 1 and 2, I'll get 3. Okay, but then you see what is happening. Since in active region the concentration gradient is so much, but because of saturation you see the concentration gradient is decreased, because you see this is a concentration gradient, right? So it is very much decreased. So since it is decreased, the diffusion force, right, diffusion force also decreased, right? The IC is because of concentration gradient, it decreased in saturation because you see the profile, the gradient is decreased, right? So IC will decrease, right or not? IC will decrease. Again, what will happen? Also, you see the IB1 is the same, because IB1 is injection of holes from base to emitter, but IB2 is nothing but recombination. Since in base I have lot of carriers, right? I have lot of carriers. The recombination will be more. You know, if you try to derive, the recombination is proportional to the area under the concentration profile. Since the area under concentration profile is increasing, or I can say in qualitatively, there is a lot of carrier in the base, so my recombination IB2 will decrease, IB2 will increase. So what is happening in saturation? My IC will decrease because the concentration gradient is decreasing. IB will increase because IB is nothing but IB1 plus IB2. Since IB2 is increasing, IB2 is the component due to the recombination, which is increased because of lot of carrier in the base. So my IB will increase. So what happened? Beta will be my IB divided by IC. Okay. So in active region, IC is equal to exactly equal to beta into IB. Right? Beta is the common emitter base, common emitter current gain. Okay. So in active region, IC is exactly equal to beta into IB. But in saturation, okay, my IC is decreasing, IB is increasing. Right? So what will happen to beta? Beta is IC by IB, right? So IC is decreasing, IB is increasing. So what will happen to beta? Here, if you see, my current IB is more. Here IB is increasing rate more compared to IC by beta. So this is my equation in saturation. Because in saturation, my IB will increase, IC will decrease. The equation IC is equal to beta into IB, which are there in active region, it will not follow. In saturation region, IB will be more and IC will be less. So IB will be greater than equal to IC by beta. So the condition of saturation will be a base current is greater than equal to IC by beta. In order to make you understand this equation, I have explained you the operation, or I can say I have told you all the stories. Let me summarize. In saturation, because both junctions are forward bias, the concentration profile, the gradient will be less. Since gradient is less, the collector current is decreasing, and since there are a lot of carrier, my recombination is increasing, so IB also is increasing. So since IB increasing, IC decreasing, I can say in saturation the IB will be greater than IC by beta. Okay, so in active, this is in saturation. In active IB is equal to IC by beta exactly. Okay, so with this information, let us solve the circuit. So you see, what is IB? This is IB. Okay, so IB is equal to V in is 2 volt minus 0.7 volt. This is 0.7. IB is equal to V in is 2 volt minus 0.7 volt divided by 12K. 12K, and IC is equal to 5 volt minus this is 0.2 is given 0.2, 5 minus 0.2 divided by 4.8K. Okay, so I know IB should be greater than equal to IC by beta in saturation, right? This implies beta should be beta is greater than, okay, IC by IB greater than equal to, right? This implies IC is 5 minus 0.2 is 4.8 divided by 4.8K, right? IB is nothing but 2 minus 0.7 is 2 minus 0.7 is 1.3 divided by 12K, right? 12K. So if I calculate this one using a calculator, what I'll get 4.8 by 4.8K is 10 power minus 3, right? 10 power minus 3 divided by 1.3, 2 minus 1.3 divided by 1.2K, 12K. So I got 9.2. Is the beta should be greater than equal to 9.2. So beta minimum is equal to 9.2. Okay. If beta minimum is 9.2, right? We know alpha minimum is equal to beta minimum by beta minimum plus 1. Okay. This is equal to how much? This answer divided by answer plus 1 equal to 0.90. Equal to 0.90. Okay, so the common emitter base current gain alpha will be 0.90, right? In order to that the circuit in order the circuit should act as a switch. Means if my beta alpha minimum is 0.90, then it will act as a switch. That means when I apply 2-volt pulse, my transistor will be saturated and it will act as a switch. Okay, this is the answer. Let us see the next question. Okay. For the circuit shown, right, assume that my NMOS transistor in saturation, right? My NMOS transistor is in saturation. If the threshold voltage VTN is 1 volt, okay, VTN is equal to 1 volt, right? Let's change the color to red. Okay, VTN is equal to 1 volt. If transconductance parameter mu1 CA double by L is 1 milliampere per volt square, okay, neglect the channel length modulation and body effect, right? So if I want to neglect the channel length modulation, so lambda is nothing but the channel length modulation parameter should be equal to 0. Under this condition, the drain current ID in milliampere is, okay. So you see, this is my gate, this is my source, okay, this is my drain, okay. Since my NMOS is in saturation, I know my current ID, okay, current ID is equal to half mu1 Cx double by L, right, into VGS minus VTN whole square into 1 plus lambda VDS. Since lambda is equal to 0, this factor will not come into picture. It will not come into picture. This is not there. Okay. So this is the current flowing from drain to source. Okay. So you see also VG is nothing but 8 volt into 5 mega ohm by 5 plus 3 mega ohm. So VG is equal to 8 into 5 mega divided by 5 plus 3 mega is nothing but 5 volt. Okay. And VS is nothing but ID into RS, right? Okay. and VGS is VG minus VGS equal to 5 minus VGS. Okay, this much we know. Now let us apply the equation. Okay, what is ID, guys? ID is nothing but Vs by 1K, right? ID is equal to V source by 1K is equal to half mu1 Cs double by L. Half is half. This much is given by 1 milliampere. So this is 1 milliampere per volt square. Okay, 1 milliampere per volt square into VGS minus what is VTH? VTN is 1 volt square. Okay. Simplest. What is VS? VS is nothing but VG minus VGS. So 5 minus VGS. Okay. Into 10 power of minus 3 is equal to half into 1 milli into VGS minus 1 whole square. So 1 milli and this get cancelled. I have to take 2 to that side. So 2 into 5 is 10 minus 2 VGS. VGS is equal to VGS minus 1 whole square is VGS square plus 1 square minus 2 VGS. Okay, and VGS get cancelled here, right? This implies VGS square is equal to 10 minus 1 is 9. This implies VGS is equal to plus or minus 3, right? And VGS, since it's an NMOS transistor, should be greater than 1 volt. So VGS is equal to 3 volt. It cannot be minus 3 volt, right? So VGS is 3 volt. Okay. Now, what is VS? VS is equal to 5 minus VGS is 3 volt equal to 2 volt, right? So what is ID? ID is VS divided by 1K, nothing but 2 volt divided by 1K is equal to 1 milliampere, right? Very straightforward question, right? So only thing is you have to know ID is equal to VS by 1K, then you have to put VG minus VGS is the VS. Okay, so if you do like this, the solution is very easier. If you do the other way means you put ID equal to ID and VGS is equal to, if you put VG minus ID into RS. If you do like this, it will take some longer time to solve. Okay, so in exam, always try to express ID in terms of VGS, because what is the other way I'm telling? Other way is you put ID equal to ID, you put VGS is equal to 5 volt minus VS. VS is nothing but ID into RS. If that you put here and solve directly, you will get ID, but the equation will be a little lengthier and difficult to solve. So always try to express ID in terms of VGS in order to solve it quickly. Okay, let us see the next question. For the DC analysis of the common emitter amplifier shown in the figure, neglect the base current. So okay, so it is telling IB is very small, very small. Okay, so neglected. Small neglected. Okay, so if IB is very small, we know IC is equal to IE is equal to nothing but my emitter current IE is equal to IC plus IB. Since IB is neglected, is equal to, this is IC, right? IC collector current is equal to IC. This is the meaning of neglecting my IB. IC is equal to IE. This is the first condition. Okay. Assume that emitter and collector current is equal. Yeah. When you neglect IB, definitely it will be equal. Given VT is equal to 25 millivolt, VB is 0.7 volt. The BJT output resistance is particularly infinity. Okay. The output resistance is resistance looking from this collector towards the downside. Okay. It will be infinity. That is good. Under this condition, find the midband gain AB is equal to V0 by Vi. Okay. So whenever we want to find the gain, we have to do the AC analysis. Okay, then you have to draw the AC equivalent model. Okay, and we know the AC equivalent model parameters depending upon my DC value, right or not? So in order to do the AC analysis first, I have to get the parameter of DC parameters. That means DC current and DC voltages. Okay, because the AC model needs DC values. Okay, so first we have to do the DC analysis. Then using this DC analysis, I will go to the AC modeling. Then I will get the gain. Okay, so the first step is using this, do DC analysis. Okay, let's do. So if I want to do DC analysis, right, all the capacitors will be behave as open circuit, right? Because I am only interested in DC, so I am assuming there is no AC present in the input. So the capacitors are open. Also, thing is, if I want to do DC analysis, right, the impedance is nothing but 1 by j omega c. Omega is 0 means it is infinity. So all are infinity. All are infinity. So let us do the DC equivalent model. Okay. So this is a 2K. This is a 47K. 73K. This is a RC is how much guess 2K. This is 12 volt. That's all. Right. So in DC analysis, I have to find the collector current and collector voltage. Okay. So BC you can say. Right. You see what I have done in DC analysis. This capacitor is open. The capacitor is open. This is open. So all are open circuited. So I have put the DC equivalent model here. Okay. Then I have to calculate the collector current. Okay. What is base voltage, guys? VB. So for calculating, first I will do VB. VB is nothing but 12 volt into 47K, right? Divided by 47 plus 73K. Okay. So let us take the calculator and see how much it is coming. 12 into 47 divided by 47 plus 73. So I got 4.7 volt. Okay. And what is V? V is nothing but VB minus VB. Okay. VB is given 0.7 volt, right? So VB is 4.7 minus 0.7 is equal to 4 volt. If VB is 4 volt, then what is I? I is VE by 2K. So 4 volt by 2K is equal to 2 milliampere, right? Is equal to IC, right? What is VC? VC is equal to 12 volt minus 2 kilo ohm into IC is 2 milliampere, nothing but 2 to 4, so 8 volt, right? So from the DC analysis, I know IC, I know VC. Okay. Now we have to do the AC analysis. Okay. So AC analysis. See, what does it mean, right? If I don't apply any signal, right, there is a collector current of 2 milliampere flowing. There is a output voltage or collector voltage 8 volt. If I apply a input signal, right, everything will be the net current. So when I apply a signal, okay, my IC will be 2 milliampere plus some signal current, right? Similarly, VC will be 8 volt plus some signal. Okay, whenever I apply input signal, what will happen? A signal will be superimposed over the DC. Similarly, the output voltage also in the output to the DC voltage, AC will be superimposed. Then I am interested in calculating the magnitude of output voltage by the magnitude of my input voltage. Okay, so V in divided by V out. This I am interested. Okay, so for doing that, I have to do the AC analysis. So in AC analysis, okay, in the frequency of interest, midband frequency, this capacitors will behave like a short circuit, right? Because it is given also. You see, in the midband gain, the capacitors will behave like a short circuit. Okay. So let us do the AC equivalent circuit. So for AC, I'll assume that there is no DC because present now I am only interested in AC or small signals. Okay. So I assume that there is no DC, only AC is present. Okay. Since but actually both DC and AC are present, for my analysis, I am assuming that I am doing only AC signal analysis. Okay. That means I am only interested in the small signals because already I calculated the DC. About it, AC will come. So now I will be only interested in the AC signals. Okay. So for AC signals, the DC will be 0. So it will be grounded. Okay. Okay. See, this will be short circuit. That means VN will be directly coming to my base to emitter. VN. Okay. Since this is short circuited, so this is ground. This is short circuited. This short. This is ground, and this is also short circuited. So this will be like a short. This will be my RL. Okay. RL is 8K. This is 2K. This is ground. This is 73K. This is 47K. Okay. Now we don't need to draw anything. Okay. From your experience, you know when there is a change in base emitter voltage, Vn will change my VB. Okay. In correspond to my change in Vn, there will be change in collector current. The AC current will be is equal to Gm is the transconductance into the VB. In this case, VB is nothing but Vin, so equal to Gm into Vn. Okay. So whenever I apply input signal, what it will do? It will go and modulate my base to emitter voltage. In this case, base to emitter voltage is equal to my input voltage. Since my base emitter voltage is changing, in response to my change in base emitter voltage, there is change in collector current. The change in collector current is nothing but transconductance time my base emitter voltage or Gm into input voltage in this case. Okay. Now what is the output voltage? The output voltage is nothing but my output signal voltage is nothing but the current IC, the signal current IC into the resistance looking at this node is 2K parallel to 8K or nothing but RC parallel to RL. Okay, is equal to IC. IC is nothing but how much? IC is Gm into Vn into RC parallel to RL. So if I want to calculate the gain means nothing but the signal at the output divided by my input signal strength is nothing but this will be minus IC, right? Current is going like this, so there will be minus IC. Okay, because 0 minus something is VC. Okay, so minus Gm into RC parallel to RL. Okay, so what is Gm? So gain is equal to minus Gm into RC parallel to RL. What is Gm? Gm is in BJT. You all of you know the DC collector current divided by thermal voltage. Okay, so thing is you see in AC gain, that this is my gain, right? This is my gain. AC gain depend upon my transconductance, and my transconductance Gm is depend upon my DC collector current. That's why I have done the DC analysis. Okay, so is equal to what is DC collector current is 2 milliampere, right? 2 milliampere. So I'll apply 2 milliampere by what is VT? VT is given how much? 25 millivolt. 25 millivolt. So is equal to 2 by 25. Okay. So what is gain now? Gain is equal to minus Gm is 2 by 25 into RC parallel RL. RC is 2K parallel to 8K. how much 2 parallel to 8k equal to 2 into 8 by 10 1.6k. Okay, minus 2 by 25 into 1.6k. Okay, so let's do the calculation. 2 divided by 25 into 1.6 into 10 power of 3. I got minus 1 to 8. Okay, 8. This is my gain. Okay, so very simple question. First thing is you have to do the decision analysis. From decision analysis, calculate the collector current. Then the gain is nothing but the IC minus IC into RC parallel RL. I know IC is GM into VN. GM depend upon my transconductance, is depend upon my DC collector current 2 milliampere by 25 millivolt. Then I apply all the values to get the voltage gain AB. Okay, let's see the next question. The amplifier circuit shown in the figure is implemented using a compensated operation amplifier. Okay, op-amp has an open loop gain of A0 of this one. Okay, A0 given 10 power of 5 volt per volt. Okay, the open loop cutoff frequency. Okay, without the feedback resistor, when it is in open loop. Okay, FC is 8 hertz. The voltage gain of the amplifier at 15 kilohertz each. Okay, so the voltage gain at 15 kilohertz. Okay, so I have to calculate the closed loop voltage gain of the amplifier. If my open loop gain is this much and open loop cutoff frequency is this much. Okay, first see, if open loop gain is this, open loop cutoff frequency is this, the open loop transfer function, right? Open loop gain transfer function AS is equal to, we know A0 by 1 plus omega by omega C. J and omega by omega C. Sorry, I can say 1 plus S by omega P, omega C. Okay, this is my open loop transfer function. Then gain is given 10/5. FC is here 8 hertz. So if I want to express in terms of SC, A0 divided by 1 plus this is nothing but how much? S is J into omega. J into omega, omega is 2 pi into F divided by omega C is 2 pi into FC. So this is equal to A0 divided by 1 plus J into frequency divided by FC is my open loop transfer function. Okay. Okay. And in open loop, V output is equal to gain into V positive minus V negative. This is nothing but AS. AS is nothing but, in other words, AS is equal to V0 by V plus minus V minus. Okay, V plus minus V minus. That's all. Okay, this is my open loop transfer function. So what is happening in closed loop? In closed loop, what happens? There is a feedback from V output to V negative. So, and this is my AS. Okay, here in closed loop also, my V output is equal to AS into V positive minus V negative. Okay, this implies ANC into, what is V positive? V positive is nothing but V in minus what is V negative? V negative is nothing but V0 into 1K by 79 plus 1K. So it is V0 into 1K divided by 79K plus 1K. This factor is called beta. Okay, this is nothing but feedback factor beta. So I can express in terms of AS is equal to S into V in minus V0 into beta. So here beta is equal to 1K divided by 1 plus 79 is 80K. 80K. Okay, so is equal to 1 by 80. Okay, is equal to my V0. Okay, now if you take V0 aside, V0 into, okay, 1 plus S into beta is equal to as into v in, right? This implies what is asking is gain, right? Gain is v0 by v in is equal to as divided by 1 plus as into beta. Okay, so we know what is as. As, let's put this one. Okay, as is equal to a0 by 1 plus j into f by fc divided by 1 plus what is as. As is a0 by 1 plus j into f by fc into beta, right? Into beta. So let us take this to downside. I'll get v0 by v is nothing but av is nothing but a0, okay, divided by this will come to bottom. I'll get 1 plus j into f divided by fc plus this 1 plus j into f by fc multiplied by here. So I'll get a0 into beta. Okay, so what I got gain av is equal to what I got above a0. Above I have got a0. Below I got 1 plus a beta plus j f by fc. Okay, so 1 plus a beta means a0 beta. Okay, a0 beta. So here you see a0 beta plus j f by fc, j into f by fc. Okay, so if I take 1 plus a0 beta common, okay, it will be a0 by 1 plus a0 into beta. I have taken 1 plus a0 beta common divided by 1 plus. So if somebody don't understand, let me do what another way. A0 is equal to, okay, if I take 1 plus a0 by beta common, okay, it will be a by 1 plus a0 beta divided by, if I take that is common, I will get 1 plus j into f by fc into 1 plus a0 beta. Okay, so since a0 into beta, a0 is given into beta is nothing but given how much? A0 is 10 to the 5, okay, 10 to the power of 5 into beta is how much? 80, 1 by 80. 1 by 80 is 10 to the power of 5 by 80 is very greater than 1. So I can neglect this one, right? You can neglect this one. A0 by A0 beta is nothing but 1 by beta in the top, okay, plus 1 plus j into frequency by fc into 1 plus a0 beta. Okay, so what I can conclude, okay, in the open loop, gain is equal to as is equal to a0 by 1 plus f by fc into j, open loop. So in closed loop, you compare this one, okay, compare this one with this one. Okay, in closed loop, the gain a0 have decreased from a0 to 1 beta. So gain decreased from a0 to 1 by beta is nothing but 10 to the power 5 to 1 by beta is 1 by 8 is 80. Okay, and bandwidth, earlier it was the cutoff frequency, I can say fc become fc to fc into 1 plus a beta. Okay, so I can say gain have decreased and bandwidth have increased by a factor of 1 plus a beta. Gain have decreased by a factor of 1 plus a beta. Okay, so now put all the values, calculate gain at the frequency given. So 1 by beta is nothing but 1 by 80 is 80. Okay, divided by 1 plus j into what is frequency? Frequency is given 15 kilohertz into 10 to the power 3. Okay, divided by fc is given 8 hertz, 8 hertz into 1 plus a0 beta. I can neglect 1 so a0 beta is 10 to the power of 5 into beta is 1 by 80, 1 by 80. Okay, so is 10 to the power 5. Okay, so is equal to 80 divided by 1 plus j into 10 to the power of 88 get cancel. 10 to the power of 10 is 10 to the power 4. This is 10 to the power 4. 10 to the power 4. So I got 10 to the power 4. 10 to the power 3 got cancel. I got 10 to the power of 3. I got 10 only. 10 1.5. 1 plus j into 1.5. right? 1 plus j into 1.5. Clear? Okay. So this is your cancel. So AB mode will be equal to 80 by root over of 1 square plus 1.5 square is equal to, let us do 80 divided by root over of 1 square plus 1.5 whole square is equal to how much? I got 44.37 is the answer. Okay, see how easy it is. Thing is ki I have to know the basic principles. Basic principle is what? The output is always equal to gain into V positive minus V negative. Okay, if I put that here, I know V negative is V0 by beta, V0 into beta. So I put all these things, then I got a gain is equal to A0 by gain equal to 1 by beta divided by this and this. So I concluded that ki gain decreased by factor of 1 plus a beta and cutoff frequency increased by factor of 1 plus a beta. Then we put all the values, very straightforward, to get the solution gain as 44.37 at the frequency of 15 kilohertz. Okay, so I think that's all. Thank you guys.